Hello, dear virtual audience. My name is Felix Langfeld. I'm from the Hamburg University of Applied Sciences. And in this video, I want to present you our contribution to the ISNVH 2020. And the topic of this talk will be about the impact of manufacturing inaccuracies on the acoustic performance of sound insulation packages with plate-type acoustic metamaterials. So I want to start with a brief motivation for this topic. And if we think about noise control applications, you know that there are in many cases acoustic partitions employed to protect some space from exterior noise. And one example in a car is the firewall, which is used to protect the passengers or reduce the noise from the engines transferred to the passengers. But you can find it in other areas of applications, for example, also in aircraft, where the cabin sidewall acts as the acoustic partitions, among other things, of course. So acoustic partitions typically have very poor sound insulation properties at low frequencies. So there is a demand for improving the performance of such partitions at lower frequencies. And one idea could be to use the so-called plate-like acoustic metamaterials, or PAM, to improve the low frequency performance. What are PAM? You see a very idealized drawing below the picture, where we have a thin film with periodically added masses to it. And these metamaterials can be very lightweight and very thin. And compared to other metamaterials like membrane-type acoustic metamaterials, they don't require any pretension or any grid structure. And if we look at the sound transmission loss performance of such metamaterials, we see that at low frequencies there is a peak in the transmission loss, a so-called anti-resonance, where the transmission loss can be much higher than the mass law. And this is what we want to exploit to improve the sound transmission loss of acoustic partitions. For example, we could integrate these metamaterial films or plate-like acoustic metamaterials quite easily into glass wool insulation packages to improve their low-frequency sound transmission loss. So the question which motivated this contribution now is, ideally these masses are distributed periodically on the film, but you can imagine there will always be some deviations from this idealization. And the question is, how do these random deviations, for example due to manufacturing, affect the performance of these metamaterials? Okay, so for this, we wanted to perform some numerical simulation, and we needed to validate this numerical model first. And for the validation, we used a metamaterial test sample that we built ourselves. You can see a drawing on the left and also some pictures from our lab to the right from the measurements. And the metamaterial basically consisted of a 0.75 millimeter thick polycarbonate film, and 180 steel masses were added to this film. So the overall surface mass density of this metamaterial was about 1.9 kilogram per square meters. And we put this in our transmission test facility between a reverberation chamber and an anechoic chamber, and measured the sound transmission loss using an intensity probe and under diffuse field excitation. So this is the experimental part that we use in the validation. And the numerical model that we wanted to validate is shown in this slide. You see on the left and the bottom basically the discretized version or the numerical representation of the metamaterial, the film and the masses. And above this picture you see also the acoustic domains. So the blue parts are the acoustic domains surrounding the sample, and the purple icons indicate that these domains have been truncated using arbitrarily matched layers to simulate fluid half spaces on both sides of the sample. And the green rectangles are the plane acoustic waves, the random uncorrelated plane acoustic waves that simulate the diffuse field excitation that we also had in the measurements. Okay, here we see now in this plot the results, and the circles or the dots in this plot are the experimental results, and the lines or curves are the numerical results. And the blue data shows the results for the metamaterial, and we have also two gray curves that are for just a homogeneous film for reference. The lower one is the film without any masses added to it, and the dashed curve is an equivalent film with an equivalent thickness, so that it has the same surface mass density. So we see that the agreement between the measurement and the simulation is very good. And we also see two arrows in this plot. These are the anti-resonances of the metamaterial that were estimated using an analytical model. And you see that at these anti-resonances we have the transmission loss peaks. And the first one is obviously much higher than the second one. So usually we focus on the first anti-resonance. And overall, as I said, the agreement is quite good. So we can expect this, or we can use this numerical model to simulate different random variants of this metamaterial. So, in studying the effect of randomized mass parameters, we looked at three different variations. So the first one I will show you here is the randomized mass positioning. You can imagine maybe there's a machine that places the masses on the film and it's not as accurate as we want it to be. And I will now show you some results of different randomizations of these mass positions. I have to note that the overall surface mass density in all cases is the same, so this comparison is fair in that sense. Yeah, and the positioning was randomized using a Gaussian distribution with a certain standard deviation, and on the left side you see how the metamaterial looks like with a standard deviation of 0. Of course, it's perfectly regular, and on the right side you see the resulting transmission loss. And now we see what happens if we increase the standard deviation to 3 millimeters, 6 millimeters, and 9 millimeters. And you see that from 3 millimeters starting, it still looks quite regular. At 6 millimeters, you see there are also already some very huge deviations. Some masses are quite close together, and at 9 millimeters, there's already more or less a chaos on the metamaterial. And looking at the transmission loss, it's kind of surprising that in the first three cases, all curves are more or less the same. They're quite similar, and only at a standard deviation of 9 millimeters, there is a very huge difference, and the whole curve looks more or less smoothened out. And if you look at it a bit closer, we see that this is very similar to damping, which affects all anti-resonances and resonances of the metamaterial. The significant effects only become visible for very high standard deviations, where you can see already with the naked eye that this metamaterial is not as periodic as it should be. Okay, the second parameter that was randomized is the mass diameter. And I will show you quickly the 4 different realizations, starting with a standard deviation of 0 up to a standard deviation of 9 millimeters. And when we now look at the transmission loss on the right side, you'd see that the effect is not as large as in the mass positioning case. So, well, there's some shifting in the first anti-resonance frequency, and also the second resonance is sort of smooth, but the effect is not as global and as large as in the previous case. Okay, let's go to the third case, which is the mass thickness. You can imagine maybe the masses are created by adding some material on a film, by, for example, some kind of plastic, molten plastic, which then hardens, and then maybe it's not always the same amount of material added to the film. Let's see what happens if we have randomized thickness. So we have the standard deviation up to 0.4 millimeters, and in this case in the left diagrams, the thickness is shown by the color of the masses, and a lighter color means a thinner mass, and a darker color means a thicker mass. Surprisingly, if we look at the transmission loss curve, there's only a very, very small effect on the first anti-resonance, but more or less the transmission loss of the metamaterial is unaffected in this case. So this is quite an interesting result. So in the paper we also provide some in-depth discussion of these results. I want to just show you one discussion of the randomized mass positioning, which was the largest influence, or the largest effect, which showed the largest effect. And for this we used analytical calculations, and you can imagine if we have masses that are more closer together, for example, then the unit cell size of the metamaterial will be smaller, and if we have masses that are further apart, the unit cell will be larger. So we can perform analytical calculations of different unit cells with different sizes and see what is the effect of the these different unit cell sizes on the transmission loss. So, and you see it here on the right side. On the left side we have the comparison with the numerical simulations of the random PAM. On the right side we have the analytical results. And I have to point out that the analytical results are for normal incidence. So the magnitude of the transmission loss will be a bit different. But we can see in the plot on the right that a change of the unit cell size affects all anti-resonances and also all resonances. And this explains why the position deviation affects more or less everything of the metamaterial and sort of smoothes out the transmission loss curve of the metamaterial. Okay, let me quickly summarize and conclude my talk. So we performed some numerical investigation of the impact of randomized mass parameters on the transmission loss of PAM. And we used an experimental model to validate our numerical model first. And then in the second part, we used this numerical model to simulate different randomized parameter effects or mass parameter effects. So the key findings are that an inaccurate mass positioning affects almost everything or every characteristic of the PAM transmission loss curve. So the anti-resonances and the resonances will be more or less smoothed out, like a damping. In case of the mass diameter, we saw that this mainly leads to a shifting of the first anti-resonance. In the case of the mass thickness, we saw that this only very lightly affects the first anti-resonance, but on the remaining sound transmission loss curve was nearly unaffected by this. So in essence, the most sensitive parameter is the mass position. However, we saw that this becomes only significant in our studied case when the deviation is already quite large, and we could see with the naked eye that there's already something wrong with it. Going back to the application of such metamaterials, we can see that there's no obvious improvement of the bandwidth of the anti-resonance by purposely introducing some deviation in the mass positioning. So we have no benefit in that regard when we have randomized or deviations from the ideally periodic structure. However, we saw also that any dips at the resonances of the metamaterial, where the sound transmission loss is decreased, can be diminished by increasing the deviations from the ideally periodic structure. However, the cost for this is, of course, that we also have a diminished anti-resonance peak, so there's always a trade-off in this case. So thank you very much for your attention. I hope you enjoyed this video, and if you have any questions, you can always write me an email. You see the email on the slide, and otherwise I wish you still a very nice virtual conference. Thank you very much.